In this video, we're going to start looking at solving exponential equations. That's what Standard 21 is all about. Now, we're going to start with an application problem to kind of motivate why we may want to be able to solve exponential equations. And this one's going to involve a radioactive substance. And so with radioactive substances, what happens is over time, they decay into other substances. So in this case, it's iodine 123, and iodine 123 atoms, they jettison parts of themselves and become a new element, essentially. But in that jettisoning, you get energy output. And so, that's why certain radioactive substances are very dangerous, is because that energy that it emits can be very damaging to anything biological. So in this case, we have this iodine 123, and it says that the half-life is 13 hours. Okay, you're going to hear this term half-life quite a bit, especially in the coming lessons. But half-life just means that it's how long it takes for half the substance to be left. So for iodine 123, it's 13 hours. So that means you have half the iodine 123 you started with 13 hours later. So it says if there's initially 50 grams of this iodine 123, determine how long it takes for the sample to decay to 10 grams. The amount of the substance left after t hours is given by this function. So we already have that function, right? They give that to us. And you can see why it makes sense, right? If you plug a 13 in for t, then you have a 1 in the exponent, which means you're multiplying 50 by a half, which would give you half of the substance left over, right? When you put a 26 in here, that would be 2 half-lives. So you should have a quarter of the substance left over, which is exactly what you get when you take 1/2 to the second power. So you can see why I think we can agree that that's the proper function to use for this. All right, but they're saying, how long does it take to get it down to 10 grams? So we know that we want this to be 10, right? What we're wanting to know is what is t when that happens. So here's our equation that we need to be able to solve. Now what we have here is this exponential equation, and the t is stuck up in that exponent. Now we're going to take two approaches to this, and so this would be over here approach 1. And approach number 1 would be to try to rewrite the exponential in logarithmic form. Now why on earth would I want to do that? The reason I would want to do that is because remember that it looks something like this. If you have b to the y equals x, then that translates to y equals log base b of x. Okay, so in this instance, it's the y that I want to solve for. And if you rewrite it in logarithmic form, then you've got that down out of the exponent and in fact all by itself. Okay, so that would be using the exponential to logarithmic equivalence. So let's try that. But one thing you'll notice is that there's no extra over here with the b, right? Right now I have this 50 over here with the base of 1/2 and the exponent. So I think a logical first step would be to divide both sides by 50. So then I can actually get the logarithm all by itself. But now this has the same form as this. It just looks a little more complicated. So to make that transition to logarithmic form, right, we know that we're going to say that the exponent is equal to the log base 1/2 of 0.2. All right. And I can finish getting t by itself if I multiply both sides by 13. So we have t equals 13 log base 1/2 of 0.2. Okay, so that's an answer, but it's not a very good one for an application problem, right? We'd like to be able to put in our calculator. So in order to do that, remember, we do have the change of base formula available to us, right? So we can say that this is the natural log of 0.2 divided by the natural log of 1/2, right? So right there, we're using this property, log base b of, and how did I write it before just to be consistent? I said the log base b of a is equal to the natural log of a over the natural log of b, right? So that's the property that we're using to get to here. And when I put that into my calculator, I get 30.2 hours. Okay? Now, what I want to do is show you a different approach as well. And the reason I want to show you a different approach is because it tends to be the way I think most people prefer to do these problems because it's kind of nice and easy to remember. And also, there are certain types of problems that you really have to do that way. So it gets a little bit tricky. So while you're more than welcome to use this method of converting from the exponential form to the logarithmic form, I'll just kind of stack the deck in favor of this other one a little bit in telling you that most people prefer approach number 2. You know, why would I even show you approach number 1? Well, it's because it's what you're already familiar with, right? We've done this kind of move of writing the equivalence a lot. All right, let me change colors here so we don't run into the other work that we've done. So here's the other approach. It starts the same as the other one in that I want to get the exponential expression by itself if I can. Okay, but what I'm going to do in the next step is I'm going to take the natural log of both sides. So I'm going to say the natural log of 0.2 is equal to the natural log of 1/2. Oops, that's getting a little messy. I apologize. 1/2 t to the t over 13. So I'm taking the natural log of both sides. Okay, why would I do that? The reason I would do that is because once you take the natural log of what's on the right here, we can then use the property that we learned that says if you have the log of something raised to a power, that power can come down in front. And so I can bring t over 13 down in front, and that will allow me to get the t untracked from that exponent. So my next step looks like this. Natural log 0.2 equals t over 13 natural log 1/2. All right. And at this point, it's just a matter of getting t all by itself. So if I wanted to get t by itself, I would go ahead and multiply on both sides by 13 on top, natural log of 1/2 on bottom. So I'd multiply that by what I have on the left side. And then I would do the same, of course, on the right side. So then I get some nice canceling here. T is all by itself, and notice that these two things are exactly the same. And of course, we also get the 30.2 hours. So this method here tends to be the one that people prefer overall. Take the natural log of both sides, and then get that the variable out of the exponent using this property, and then go from there. One of the advantages of this is there's no change of base formula needed, because if you take the natural log of both sides, then it's already in that form that can be typed into your calculator. All right, so that started off with a pretty complicated problem. Let's take a step back and do maybe a couple easier ones. But first I want to just talk about guidelines, okay, for solving exponential equations. Okay, so number one, isolate the exponential expression if possible. Number two, take the logarithm of each side, then use the laws of logarithms to get the variable out of the exponent. Or we can rewrite the exponential equation in logarithmic form, right? So those are the two methods we talked about, and then of course solve for the variable. All right, so in this example here in number two, this one, the exponential's already by itself. So if you're going to do the take the natural log of both sides approach, then you're going to say the natural log of 3 to the x equals the natural log of 14. That can come down in front. And then the thing you got to remember here is that, and I didn't really do a good job of stating this on the last page, the natural log of 3 is just a number, right? It looks kind of scary because, you know, you got this L and N there, but the natural log of 3, that entire thing is literally just a number. And so if you have an x times a number, you definitely want to divide by it to get the x by itself. So that gives us x equals the natural log of 14 divided by the natural log of 3. And by the way, I want to do a good job in this section of really distinguishing between exact and approximate, because I will ask you to do give me the exact answer and give me the approximate answer. So exact is this, right? No rounding has been done or anything like that. Approximate is where you've pulled out your calculator, right, and given me some number that's been rounded. All right. Now, just as a side note here, what would the other approach have been? The other approach would have been to rewrite this in logarithmic form. So I would have said x equals the log base 3 of 14. But of course, the change of base formula would allow me to get it in a position to put it in the calculator, just like that. So if you, you know, just generally, if I'm just asking for the exact answer, I'm okay with this, or I'm okay with this, right? Either one of those is fine. So one of the things that you'll encounter in these problems is that, especially if you're like doing a study guide that I've produced and I show you a solution of mine, it's possible that our solutions will look a little different, but they very well may both be correct. And so that's where, you know, typing it in and getting the approximation is good, because you can double check that, you know, your answer is the same as mine. All right, let's do another one here. So here we have 2 times 5 to the x minus 3 is equal to 14. So I look at this, I might be tempted to immediately take the log of both sides, but let's remember, number one is isolate the exponential expression if possible. So before I go taking the log of both sides, I want to start by getting the exponential by itself. So this will be 5 to the x minus 3 equals 7. And now that the exponential expression's by itself, now it's appropriate for me to take the natural log of both sides. And by the way, let me just actually say this. The common log is totally fine too. Okay, it doesn't matter. So if I use the log, that has a base 10, there's nothing special about the natural log. I don't know, I tend to favor it for some reason. But this is totally correct here. But the big thing is, what do we know? Once we have the log of something to a power, that power gets to come down in front. Now be careful when you do this. This entire thing has to come down in front and multiply by the logarithm. So it's important to put that x minus 3 in parentheses when there's multiple terms up here. So when it comes down, it'll be the log x minus 3 times the log of 5 equals the log of 7. All right, now if you wanted to, you could distribute this through to both of them. That would be totally fine. I kind of like the idea here of immediately getting rid of the log of 5. Right? If I divide by it before I ever distribute anything through, then I just immediately get it off of that side. And so I'm left with x minus 3 equals the log of 7 over the log of 5. And then the only thing left is to add 3. So log of 7 over the log of 5 plus 3. And if I put that in a calculator, it should spit out about 4.21.